Welcome to this video reviewing the DC Circuitry half-term assessment. So I'm going to start off with some fairly basic questions. So we've got a 12 volt 36 watt lamp is lit to its normal brightness using a 12 volt car battery that has no internal resistance, and it's switched on for an hour. Calculate the energy supplied by the battery. So first off, we need the equation. So we've got the power because it's given to us here because it's watts, so we know that's the power. We've got the time, so we can use the energy as power times time equation. Put those in, substitute your values. In this case, you get this answer here, and 36 is a two significant figure number, so two significant figures would be appropriate for the answer there. Okay, so the next one wants us to work out the total number of charges that are passed through the lamp. So we've got energy, we just calculated it. We've got potential difference, so we can calculate charge using this equation here. Notice again another mark for stating your equation in rearranged form. We've got numbers substituted in, and in this case there's a mark for showing that as well. You get this value here, which to two significant figures, because 12 is two significant figures, is 1.1 times 10 to the 4. Then it wants us to calculate the number of electrons that pass through. So we know how many coulombs have passed through, and we know that one electron is this many coulombs. So all we have to do is divide by the total number of coulombs by the number of coulombs for each electron, and we end up with this value here. Those of you who happen to know how many electrons are in a coulomb, you could also do it that way. That would make no difference, but this is the way I would approach it there. Okay, so that completes question 1, fairly straightforward. So for question 2, we've got a diagram showing an electrical circuit, and we've got a battery again, negligible internal resistance. First question was to show that the current passing through the 120 ohm resistor is 25 milliamps. So that's the current going along this section here through A. So what we want to do is we've got the potential difference across this whole section. That's 8 volts across here. The total resistance is 320, so 200 plus 120. By doing the ratio of those two, that would give us the current. So there's a mark here for showing the equation you're using, another one for showing the value substituted incorrectly. They've given you the answer, so there's no mark for the answer there. Okay, so that's the current through that one. Then it wants us the potential difference across the resistor 120. So I used Ohm's law. I've got the current, I've got the resistance, so multiplying those two together would give you the potential difference across 120. Alternatively, you could have used your potential divider equations and done 120 over 320 times by 8 again would give you 3 volts as the answer. It's only worth 1 mark, so you just have to get 3 volts, and that's your mark. Okay, so that's that one. Let's carry on with question 2. So explain why a voltmeter connected between the points A and B will read 0 volts. So a voltmeter measures potential difference. So if your voltmeter says 0, what that means is the 2 points you've plugged your voltmeter into are at the same potential. So what I've done is worked out what the potential is at A and what the potential is at B. So this first one, we've already worked out the potential difference across the 120 ohm resistor in the circuit. So the potential starts at 8 coming out of the cell. It loses 3 across the 120 ohm resistor, which means there's 5 volts of potential left at A. For B, we're going to work out the potential difference across the 600, and this time using a potential divider equation. Again, same process, subtract that from 8. That tells us the potential at B. And what you'll notice is these two values are the same. They're both 5 volts. So the potential difference is 0 because they're at the same potential. This is a question for those of you who are pitching towards being 8A star students. This one is where you get to really demonstrate your understanding of circuit, but once you've seen a few of these, you'll start to get the idea. The circuit you're actually looking at actually has a name. It's called a Wheatstone Bridge, and in this case it's got a balanced Wheatstone Bridge because you get a current of 0 between them, or potential difference of 0 between them, but that's just a fun side fact. Okay, so moving on to question 3, we've got a circuit containing a battery of EMF 12 volts, 2 resistors and an LDR. And we've got an ammeter in there and a switch, and again your battery has no internal resistance. Lots of assumptions being made, never mind. So the switch is open, so we can see that disconnects the LDR from the circuit. Show that the potential difference between points X and Y is 7.5. So I'm going to use a potential divider equation. It's the quickest way to the answer. So this is the general form of it. So we want to know the potential difference across X, Y. So we put the resistance of X, Y on the top, which at the moment is 200. And then the total resistance is 200 plus 120, so that's in your bottom line. The EMF is the potential difference across those two resistors, so we'd multiply by 12. We've got a mark for showing the number substituted in, and the final answer is 7.5. Again, there's no mark because it's a show that question. You could have also done this by doing the EMF divided by the total resistance to get current, and then use the current to do this, but you can do it in one step with the potential divider equation, so do that. Okay, so next one. So we've closed the switch now, so we've actually connected the LDR in parallel with the 200 ohm resistor. Describe and explain the change to each of the following when the intensity of the light falling on the LDR is increased. So when you close the switch, what's going to happen is you've connected a parallel component in. So the current supplied by the battery is going to increase because total resistance is going to decrease. But this question is not interested in that. It's interested in, okay, you've done that. Now what we're going to do is we're going to increase the light intensity. So increasing light intensity decreases the resistance of an LDR because it releases more charge carriers to carry your energy through the component. So you're going to decrease the total resistance. Your EMF you're supplying to the circuit is the same, so if you decrease resistance for the same EMF, you're going to get a larger current, so your ammeter reading is going to increase there. Potential difference across X, Y. So I actually deal with this by looking at the one that's not in parallel because it's more straightforward. So I'm going to focus on this 121. So we just talked about the fact the current in your circuit coming around here, coming out your battery, has increased, which means the current through the 120 ohm increases. So using Ohm's law, if the current through that resistor increases, its resistance is the same, the potential difference across the 120 ohm resistor increases. And because the sum of the PD potential differences equals the sum of the EMFs, that's Kirchhoff's voltage law, that's going to mean the potential difference across X, Y will decrease if the potential difference across the 120 increases, because they still add together to give the same number. You could also answer this question using a potential divider, but I think this is a straightforward enough way to do it. Okay, so that finishes question 3. So we now got a potential divider, another one, but this time we're going to use it to measure temperature. So that's why we've got a thermistor stuck in your circuit. We've got an NTC thermistor, so as temperature increases, the resistance is going to go down. We've got a voltmeter in parallel with a fixed resistor. So we want to describe and explain how the voltmeter reading changes as the temperature of the greenhouse increases. So what's going to happen is you increase the temperature, the resistance of the thermistor is going to increase. That's your first thing. Increase, decrease, what am I talking about? What a nutter. Okay, so the resistance of your thermistor decreases when it gets hotter. This here is a potential divider equation looking at the potential difference V across R. So that's why R is on the top line. So the only thing that changes in here as it heats up is the bottom line gets smaller. So what's that going to mean? Well, it's going to mean that the potential difference across your the R is going to increase. So I don't know why it says decrease there. So let's get rid of that and let's actually do that correctly. it's going to increase there. And the reason we can do that is because this R stays the same, this R stays the same, the EMF stays the same, so the only thing that changes is this one, therefore the only thing that this one is going to increase if this one decreases. And you'll see the next part. So current, that's actually rubbish, it's not going to decrease, current is going to increase. And your EMF is indeed going to stay constant, and then likewise potential difference you're going to measure is going to increase. So we end up with the same answer, which is always reassuring. And either of these methods to explain it would be fine. Neither of them are better than the other, really. Okay, so that's that one. So if the EMF supplied is 10 volts and the fixed resistor is 5 ohms, thermistor is 15, determine the current in the circuit. So we're going to put the EMF supplied, 10, over the total resistance, 20, giving you a current of 0.50 to 2 significant figures, amps. So that's your current. We actually measure the current to be 0.45 amps. Suggest 2 reasons for this, rather than the 0.5 we've just calculated. So we've ignored internal resistance in the battery. That would act to increase total resistance, decreasing current. If temperature increases, the component fixed resistor's resistance will increase, again decreasing current. If your ammeter has non-zero resistance, that would give you a smaller current. Wire resistance, again smaller current. Contact resistance, again smaller current. Those things would all be essentially helpful here and give you an idea of what's going on. Okay, so those things would all affect your results. So let's move on to question 5. Okay, so question 5 is a design experiment question. So we have to write up an experimental method. And this is a practical you should all have done because it's one of the required practicals as part of the course. And it's generally speaking a very good one to do. So the first thing I would say is I'm going to use an ohmmeter to do it, but you're perfectly happy using a voltmeter and an ammeter. This way is just much simpler to talk about, so I've gone with an ohmmeter. So what we've got is we've got a piece of wire sellotaped to a meter ruler. You've got it fixed to the ohmmeter at one end, and then there's a crocodile clip that's free to slide up and down to change the length of your wire. So that's basically what we're going to do. So the general method is we're going to measure a 1 meter length of the wire and sellotape it to our ruler. That's our first length we're going to use. And the first thing we're going to do is actually measure the diameter of the wire. We're going to use a micrometer to do that because that gives us a very precise diameter. And we're going to measure it in a few different locations along the wire and get an average diameter and calculate the cross-sectional area using pi d squared over 4 because we've got the diameter. Okay, so now we're going to crocodile clip the ohmmeter, so there's a distance of 1 meter between the crocodile clips, and we're going to measure the resistance using the ohmmeter. And we're going to do that a couple of times so that we get average resistance for 1 meter of wire. And we're also going to repeat that process at 0.9 meters, 0.8, all the way down to 0.1. So we've got something like 8 or 9 different readings, and we're going to have repeat readings of resistance at every distance. And then what we can do with that is we plot a graph of average resistance against length. So the equation that governs this experiment is this one here. So we changed the length, so that's your x or your independent variable. We measured resistance, so that's like your y or your dependent variable. So that means the gradient is resistivity divided by the cross-sectional area. So that's why we measured that earlier. So to get resistivity, you multiply the gradient by the area, and hey presto, you've got resistivity. So an important thing here is resistivity can change with temperature, so during this experiment you're going to need to make sure you keep temperature change minimized. So that's why you stick a switch in your circuit, turn off your current between readings. That's going to minimize that effect. You might also put an external resistor in your circuit to have the same effect there, keeping current low. Okay, so that's your experimental method. Let's go on to the last question. All right, so this last question on uncertainty caused a lot of problems, and the main problem being people didn't seem to remember that to calculate uncertainty, you take the range of repeat readings and divide it by 2. So if we want the percentage uncertainty in the potential difference readings, we need the uncertainty by doing range over 2, and we need to divide that by our average value of potential difference. So the biggest minus the smallest, that gives you your range, divided by 2. This gives you your average potential difference here, times it by 100, and that gives you a percentage uncertainty which you should state to 2 significant figures. Same process with your current here, so exactly the same going on, and again giving your answer to 2 significant figures there. So those are your 2 percentage uncertainties. You need to remember, if you've got repeat readings, you shouldn't just use the resolution as the uncertainty, you should calculate what the actual uncertainty is. Okay, so then it wants us to use those values to determine the external resistance in our circuit. So the thing to know here is the external resistance is going to be the terminal voltage divided by the current in your circuit. So we're going to need the potential difference in current values to determine R. So their percentage uncertainties are going to be added together. That gives you the percentage uncertainty in R. We can calculate our value of R, remembering the current is in milliamps, and that comes out as a value of about 8.38 volts. And so it asked for the uncertainty. So again, a common mistake here is people left it as a percentage uncertainty, not an uncertainty. So we got the percentage times it by the value we've just calculated, divided by 100, gives us a uncertainty of 0.13 ohms. So that means it's 8.3 plus or minus 0.13 ohms. So the last part, so other than obtaining more precise measuring equipment, suggests a method by which the uncertainty in the resistance value could be reduced. So a lot of people said here, take repeat readings, but if you look up here, we've already got repeat readings, so that's not going to be a valid answer here. It often is, but not because we've already got repeat readings. So if you want to decrease percentage uncertainty or improve accuracy, what you need to do is have larger values. So a larger potential difference, a larger current would both act to give you smaller percentage uncertainties in those, giving us then a smaller uncertainty there. So that's the strategy you're going to want to go for, and typically going for larger values is a good answer to this kind of thing about minimizing uncertainty. Okay, so that concludes this exam paper. I hope you found these solutions useful. If you've spotted anything that doesn't make sense or incorrect, please do comment and let me know. But as always, thank you very much for watching.